Why the standard normal is so special? Because to calculate the area under the curve, if you want to know a probability, mathematicians came up with a table, right? So if you want to calculate the area under the curve, to know, for example, what's the probability of having some value of this variable less than, I don't know, 160 centimeters. You would have to integrate, you would have to use calculus, but mathematicians came up with the table, which we call the z-score table. And the z-score table gives me the probability just by assessing and reading the table, okay? So if you want to know what's the probability of z, your variable, assuming a value less than 0.72, you just come up at the table and you'll find the first decimal, which is 0.7, and then in the column you find the second digit after the decimal, so it's 0.02. You cross the rows in the columns and you will find this figure here. This figure is the probability, okay? That's what we saw in the last lecture. Okay, but we saw what I left with a question last lecture that was, if you think about this table starts at z being 0, 0. So the first area that this table gives me is a 0, 0. Jesus, okay, here. So the first area that I have in the table is this one, is the area of being less than or equal to 0, okay? What if I want the probability of being something less than 0, like 0, like minus 0.3, okay? I don't have in that table. Actually, I do. There are lots of tables that have the negative z-scores, but they won't facilitate. They will make you calculate this by tweaking the table, okay? So there are several ways to tweak this table, but there are two fundamental rules, okay? The first one, actually, before seeing the rules, let me just tell you this. If you want the area under the curve between 2 points, okay? If you want the area under the curve between 2 points, A and B, you just take the probability of being less than B, for example, minus the probability of being less than A. Think about this. If you have this area and you subtract this little flap here, if you subtract that little flap here, right? If you take that out, take this out, take out, you are left with what you want, okay, which is the blue curve. So the histogram, or the smooth curve, the squiggle, is you can look at the table to find the probability, but the table will always give you something smaller than. If you want to find something in between, you just look up two values in the table, okay? The first value of z being less than b here, and then you take out this part here, which is the probability of z being less than a, okay? Yeah.
So, like, can you just repeat what you said, like, about this, just like in words, what it is? So, like, we're subtracting.
So, if you want to find the probability of this random variable being in between, this is the area under the curve, right?
Yeah.
So, if I go to the table, I won't have in-betweens. I will have only less than, right?
Yeah, so you're subtracting.
So I'm subtracting. I'm taking the probability of z being less than b,
Okay.
which is everything here, okay? And I'm taking off this little part, which is the probability of z being less than a.
Thank you.
Okay, so you're left with what you want. All right. Now, to tweak a little bit more of the table, there are two important properties of the z variable, or the standard normal. The first of all is that the total area of under the curve should be equal to 1, right? So the total area under the curve should be equal to 1. So if you have this purple part plus the green part, if they kind of are complementary, you will have to have these probabilities equal to 1, because the area under the curve, the total area under the curve, is 1. And this concept comes from histograms, right? If you remember histograms, the area under the histogram has to be equal to 1. Okay? And the other property that is very important is the property of symmetry. So this means that the graph is actually, if you take the left part of the graph, it is mirrored with the right part of the graph, right? So it's what we call symmetry. So in the end of the day, if you want, take a look at this. If you want this blue area that I'm passing the pen here, it is actually the same area if I go to the other side, okay? It's the same area. It's the same amount of stuff that fits the blue. It's the same as that fits the orange, okay? And this will actually allow us to calculate things that are not in the table, okay? So for example, let's say that I want to calculate z being greater than z2. Okay, so I want to calculate the area on the right. I want to calculate this area here. Do I have the greater than something on the table? I don't, right? So the table, the z-score table, will always give me values. So this is the z table. Will always give me values that are smaller than, okay? So if you want a greater than, one thing that you could do is find the same area on the other side and say, well, this area here is equal to this area here, and I can calculate this little area on the left by finding it on the table. How? Well, it's just the probability of this being less than z1, and that I can find, this figure here I can find in the table. Okay? So these are concepts that we will do lots of exercises so that we can do this. But let me show you something like this. Let me just get rid of this. This was for the other section. Sorry. So let me ask you this. And we're going to summarize, okay, what you should do. I want to know what's the P of Z here. P of my Z being greater than little z. So I want this area, right? I'm shading this area. I cannot look at the table because the table doesn't give me this information. Okay, at least not the table that you will be handed in the test. Okay, so there are two possibilities here. The first one, I can find the symmetric area. Okay, so this is minus z because it's symmetric. And I can say, well, this is P of z less than minus z, and then I can go to the table. So here I cannot use the table. After I do this modification, I can go to the table, okay? But I could also say that if you think about this, this is the whole curve, it's the whole area minus, so if you think about the whole area is the yellow, what should I take out to have only the this part here that I want, right? So one way to do it is take your whole area and exclude the part less than little z. You will be left with what you want, okay? So let me just, this is too too much things here. So one of the other options is, if you want this little area, take the whole and remove, just remove this part here, okay? So I'm coming here and I'm removing that part. I'm going to cut that, remove it, and find this little area, okay? Cool. So this is something that you can also do, which is take the whole area. What's the probability of the whole area? What the whole area means? 1, right? Minus the probability of your capital Z being less than Z. Okay? Cool. So these are kind of formulas that we will have to kind of be comfortable with. Okay? Now, there is a summary that I like a lot that we can do. So if you perform exactly 2 of these operations to a single probability, then the new probability will be equal to the original. Okay, so let me put it this way. So let's say, let me draw here, that you want this area. This is little z, okay? So I want the probability of that being greater than z. I don't have that in the table. If you don't want to reason the 2 choices that you have, you can come up to this table here, like to these 3 figures, and say I have to do 2 of them. So for example, I can first subtract the whole expression from 1 and change the sign of z. So if I do that, 1 minus p of z, this is equal. Okay? Or I could do subtract the whole here, this action, and then as a second option I could flip around the inequality. And we saw that this is already, like, this is something that we know how to do. It's all of the area minus the area under z. Okay? So this is equal, this is equal. What else could we do? You can choose 2 of them. If you choose 2 of them, you will end up in equal expressions. So for example, let's flip around the inequality. I'm going to flip. So it's flipping the inequality means this. If this is greater than, I will flip to be less than, and I can change the sign of z. Okay? So this one we also saw that is valid because you can find the area that is symmetric and calculate the area under that part. Okay? So if you don't want to think too much, you could like memorize these 3 steps, and then you can do some kind of combination between these steps. Okay? Yeah.
For the second one, when you say 1 minus just the second one that you
Yeah.
got there, couldn't you just find it directly from the table? Like, why would you have to subtract it from 1?
Oh, okay. So that's a good question. Think about this. If this part here, this here, you don't have it in the table, right? You don't. You got that? Yeah. So if I were to calculate only this, the part that is, you want the pink part, but being less than little z is actually the yellow part. This is what you don't want. Okay? So you don't want the area that is less than little z. You actually want the pink one. You want this one, right? So what you're going to do, you're going to take everything and subtract the yellow part. You will be left with the pink one. Okay? So imagine that you have a scissor and you go to z. You have all the curve and you cut the curve before z. you will be left only with the little piece on the right. Okay? Good? All right. Okay, so, I mean, it's up to you if you want to kind of memorize these 3 steps and just choose 2 of them. Or you could just reason what are you doing by sketching on the side, your z-curve and trying to have some insights on what you should do with the table. Okay, so I'm going to do some exercises with you right now. Okay, so here we have, let's practice. Here I want this area to the right, right? There are 2 options. And I will reason first, and then we will see that my reasoning is actually always choosing 2 of the 3 options. So my reasoning is, if I take the total area, okay, so let's say that my total area is the yellow. If I take the yellow and I subtract the blue, if I subtract the blue part here, I will be left with that the area that I want, which is this little one here. Okay? This is the area that I want. Okay? So what does this mean? Well, the probability that my variable is bigger than 1.36 is actually the area under the curve, the whole area under the curve, which is 1, and it will always be equal to 1, minus the blue area here, right? Okay, so what is this blue area? Well, the blue area is just the probability that z is less than. It's the area that is under the curve up until 1.36. So it's less than 1.36. Okay? Now, if you do this move, you can find it directly. You just go to the table and you find this directly. Let me open a z table. Let me see if I have these values here in my z table. I don't have 1.36. I will open a z table here for you guys. Let me z score table. Let's go to this one. Okay, so this is a z-score. This is a negative z-score, which would solve most of our problems, but you won't be given it. Okay, so let's see the positive z-score. So the value was 1.36. So what are my first digits? It's 1.3, right? And then I have to go to the column and find the 006. So 006 is this one. I'm going to get down to the row of 1.3. Here you go. Okay, so I found my probability. Is this the probability that I want? No, this is just part of my operation, right? I will copy this value, 9131. So this is 1 minus 0.9131, okay? And this will be, I don't know, like near 0.8 something, 69, something like that, okay? So this is approximate, yeah.
So if we're trying to find like the z that's less than 1.36, you wouldn't have to subtract.
Yes, no, if you take a look at what the z table means, the z table will always give you the green area. So whatever z you're talking about, the figures that are on the table, they're always the area less than that. So it's directly, just reading directly from the table.
If this was on the test, would we have to calculate what it would be after we subtract, or could you just write 1 minus 0.8?
If it's an open question, I don't mind if you leave it this way, 1 minus, but if you're in the multiple choice, you will have to find the answer. So you'll have to do the subtraction, I guess. Okay? Cool? Okay, so This is 5, okay. 5, 9. All right. So the other option that we have is, what did I do? Think about all the 3 options that I had. Well, first I subtracted the whole expression from 1, and then I flipped around the inequality sign, right? This was what I did. Okay? You could have done the other option, which is, let me take 2 other actions. First of all, I want to flip around the inequality and change the sign of z, for example. So the p of z equal more than 1.36 would be flip the inequality. So if this is bigger than, I will flip to smaller than, and then I'm going to change the sign of z. This is equal, but does this move help me? Does this move help me? You could calculate from that, but do I have negative values of z in my table? No. So it is a fact that you could do option 1 or you could do option 2. Okay, it is a fact. But there are some moves that won't help you. Okay, so you will have to kind of, reason a little bit about what kind of move will help you. I don't have a negative number in my table. So this move, particularly this move, won't help me. Okay? All right. So let's do the other part here, the second exercise. So let me just leave it here. This move does not help me. Okay? Now, let's do the other one. I'm leaving this slide there, so this comment on the previous slide. Let us do this one here. So this one is the probability of z being less than, right, minus 0.17. Okay? This one's a little bit trickier, but you'll see that if you choose the right 2 steps, you will get there. Anyone has an idea of what should I do? I'll give you some options. Let's say that first I'm going to subtract all the area from this area here, okay? So all the area minus the dashed area gives me the blue one, right? If I do this, this will be P1 minus this. Did that help? Yeah.
You would take the positive 0.7.
Yeah. Yeah, you got it. So does this move help me? No, because I don't have the negative in the table. So this is not a move, although it's tempting to just like do the 1 minus, sometimes it just doesn't help. What other move that we can do? So this one doesn't help. Other move that we can do is this is equal to, well, let's flip around the inequality, and we did already this too, right? We subtract the whole expression. We flipped around the inequality. But one of them that we could do, and this is interesting, is this. You could subtract the whole expression from 1 and change the sign of z. So you subtract the whole expression, and then you change the sign of z. Okay? This helps you. This will give you the number. Okay? And if you think about graphically, what are you doing? So what are you doing? You're doing this. You're taking this area here. You're getting the 0.17, the positive 0.17, and you're removing this area here. Okay? So then you can just go to the graph and look at that. So where's my table? My table is 0.17, 0.17, 56.75. Okay, so this is 56.75, and just we can do this. This is 15. This is 43.15, if I'm not wrong. That 25, sorry. Okay. All right. So lots of exercises. Let's do lots of. Next week we'll do at least 5 different practices so that we can practice. You could, if you take a look at the past tests, there are lots and lots of exercises that you will have to flip. You'll have to find 1 minus, you have to flip the sign, you'll have to find the same area. So it's kind of just a practice. Okay? Oops. All right. So this is all I wanted to say about the standard normal. So the standard normal is a special one because we can find the probabilities just by assessing the table. Okay? But in the real world, if I'm going to draw each one of you asking our heights, the mean won't be 0 and the standard deviation won't be 1. It will be a normal. It will kind of be a bell curve because most of the population will have a height of, I don't know, 160 centimeters. And you will see less people in the extreme, right? But it's not a standard normal. It's just a normal. Okay, so how can we calculate the probabilities of curves that are not the standard normal? Okay, so let's say I have this normal here. It's not a standard normal, but I want to calculate the area under the curve. So let's say that this is the length of I don't know. Oh, this is the height of kids less than 4. So this is in tenths of a centimeter. So this is 70 centimeters. I want to know the probability that my son what's the probability that the height is less than 70 centimeters, okay? How can I do that? I don't have the table for this particular distribution, for this particular density. So what we're going to do is we're going to do just a little procedure, like a little operation, and that is called standardization. So I will standardize my bell curve, okay? So how can I do that? Well, let's say I want the probability of my z being less, not z, let's say x, right? This is x. So x is the height of a kid less than 4 years old, okay? And we know that it has a mean of 70 and a standard deviation of maybe 10, or 10 maybe is too much, 8, I don't know. So you have a normal that has a 70 with a standard deviation of 8. Okay? So I want to know, this is x. This is my variable x. I want to know x being less than a little x. So I want to come here and select a little x, and I want to calculate the area under the curve. Let's say that this little x here is 60. Okay, so in the end of the day, I'm talking about the probability of x being less than 60. Okay, it's the probability of my son measuring less than 60 centimeters. Okay, he's super tall, so it's zeros. So what happens is, if I will do a trick, okay? What am I going to do? I'm going to transform the x into a z, okay? And the thing that the mathematicians discovered is that if you take from your x the mean and divide by the standard deviation, actually this is z. This is the standard normal, and I'll show you why. And this, if I do this operation on the left-hand side of x, I should do in the right-hand side so that I don't change the inequality. Okay? So in the end of the day, what I am doing here is called standardization. I'm taking my variable x and I'm doing an operation on it. I'm subtracting a value, dividing by another value, and this new random variable is the standard normal, and this value here will be your little z. Okay, and then you can look up in the table. So this you will look up on the table. Why is this true? So let's just do it on practice, and then I'll explain why this is true. So if I have the probability of my x being less than 60, I want to transform x into z. So I will take off the mean of my distribution, which is 70, and I'll divide by the standard deviation, which is 8, okay? I'll do this on both sides, so 60 minus 70 over 8, okay? Cool? And this, in the end of the day, this newly generated variable is the standard normal, and you can calculate this value. This will be minus 10 over 8 will be the value that you will look. So this is minus 5 over 4. This is, I don't know, 0.8 something. Sorry? 1 over 8, 1.25. That's it. Okay, so this, I'll put the results here. 1.25, but it's negative. So you're left with calculating this probability, and you can look that up on the table if you tweak it a little bit, right? So we know how to tweak it. Okay, we know how to tweak this. Now we know how to. Okay. Now, why does this work? Why does this? Oh my God. Why does this work? We have to check, right? Let me tell you why this standardization operation works. So this standardization operation works because so think about this. You have a normal that it's here in 70, okay? And let me do it this a little bit. You have a normal that has a center in 70. Do you agree that if you take this curve, if you subtract to this curve 70, where is the center going to land? At 0, right? So you're shifting. When I subtract the value 70, I'm shifting this and putting it here in the center, right? So from every value of x, I take off 70. So this point will land on 0. The point 71, if I take 70, will land on 1, right? And so on. So when I subtract a value, I'm shifting the curve. Okay? Cool. What else do I do? So I subtract that value, and now I divide the new curve. So I'm dividing the new curve. the x minus mu over sigma. So the x minus mu, the new curve, I'm dividing by sigma. Okay? So when I divide something, I'm actually doing what? I'm squeezing or I'm opening the curve. Okay? But think about that. If I divide by the standard deviation, what I am doing is I'm making the curve. If I multiply the curve by 2, right, I would be doing this. If I divide the curve by 2, I'm doing this, right? If I divide, so I'm squeezing or I'm pulling or squeezing the curve. So when I divide by the standard deviation, the final standard deviation will be 1. So you're actually getting a non-normal, you're shifting it to 0, and you're spreading or squeezing, depends on the value of sigma, you're spreading or squeezing the curve so that it matches exactly the z. Okay? Now, if you do this in one side and you do it the other side, the value on the right-hand side here will be accompanying, right? So the value was here, the value was little x. If you do all these operations in little x, you will have a value that will give you the same area on the z curve. Okay? So this is called standardization. I will show you a video just in a bit. I'll stop the lecture a little bit to show you 2 videos. But this is the procedure. Just take out the mean, just subtract the mean, and then just divide by the standard deviation. Okay? All right. So let's do an exercise. I keep losing. Okay, it's here. It's here. Okay, yeah.
So like if we had a long answer question on this, and sometimes I get confused with whether to put like z is greater or less than at like the end of these types of questions, would we get marks off of that?
Well, it depends on the question, right? You have to understand what it means to be greater than or smaller than, right? And it's just like the area under the curve. So smaller than means to the left of that number. So if I do smaller than z, I want this area. Okay? If I do greater than z, then I'm at the right-hand side of the point that you're talking about. Okay? But we will practice a lot. Okay? So let's do this one. Consider a normal distribution x with mean mu equal to 12 and a standard deviation of 4. So if you think about the normal, the standard normal would be sitting on 0 with a standard deviation of 1. You're talking about a curve that is actually sitting there on 12. The center is sitting on 12. And it's 4 times more spread. Okay, so that's what you're talking about. Now I want to find what's the probability in the curve of x. So this is x, and here is z. Okay, the standard normal is here, the x is there. Okay, so they're sitting on different numbers on the number line. Okay. They're centered in different numbers on the number line, and they have different, I don't know how you say the width, okay? So what I want now is the probability of x being less than 15. So 15, it might be here, okay? What is less than 15? What area am I interested in? It's this area under the curve, right? The under the curve of x. Right, the area that sits under the curve that is less than 15. Okay? This is the area I'm interested in. I don't have a table for this. I can't go to the z table and look at the z value, because this is not a z distribution. This is not the standard normal. So what I have to do is I have to apply the standardization procedure. So P of x less than 15 will be, well, let's standardize this curve. First of all, I'm going to take the curve and I'm going to subtract 12. So I'm pushing the curve. I'm pushing here. I'm pushing the curve to 0. Okay, so when I subtract the 12, every number will land there. But you would have so this is the first step of the standardization. You would be taking the curve and bringing it up here. But I still have a curve that is 4 times wider. So what do I have to do? Well, take all the values and divide by 4. Divide by the standard deviation. And in the end of the standardization process, this new curve will sit exactly on the z curve. Okay? So you will be talking exactly about z. If I do this in the left-hand side, I have to do this in the right-hand side. Right? So I take 15, I take out, subtract 12, divide by 4, and in the end of the day, I am left to look at the table, because now this is z, I standardized. I will look at 0.75 at the table, because 15 minus 12 is 3, 3 over 4 is 0.75. Okay? And we can do that. Let's open the table, because I don't have to tweak this probability. Thank God, right? This is a smaller than and the positive number. So I can go directly to my z table and look at it. So if I go directly to my z table, the first digit is 7.7. The second digit is 0.05 to form 0.75. So I will match the row and the column. And here is my probability. The probability is 0.7734. So 0.7734. Okay? Did you understand the less than now? Like the...
Yeah, I understood that. I just don't know when to flip it for these questions.
Yeah, so if this is a negative number, you would have to tweak it, because you don't have this negative in the table. You don't have negative columns or rows in the table. Okay? So then you would have to flip it. Okay? Actually, you could flip it, or you could subtract to 1. I mean, just choose 2 operations from that 3 options and see what helps in terms of getting to the table. Okay? All right. The last thing that we're going to see is something that we already saw. So like we already did it. I just want to kind of make it official. Like, it's approximation. We did exercises about good approximation, right? So you have discrete variables that has discrete histograms. You have that bins, but maybe you don't have the values of the bins. You don't have the area, and you know that you have a smooth squiggle that fits the histogram perfectly. Do you remember that? It's the same thing. Now we're going to do the same good approximation using normal. Okay. But the concept is the same. So it's this. There are several variables that are discrete, okay? That has, if you do the histogram, if you do the bins, you will have a kind of a bell curve, Okay? So if you think about this discrete histogram, a bell curve would fit perfectly. So a bell curve would be what? A good approximation, right? So a bell curve in a continuous random variable here of a bell curve would be a good approximation. Okay? So what types of discrete variables that have this almost a bell curve characteristic? Binomial. Do you remember the repeated trials? If you repeat trials lots of times, and you make lots of bins, all of repeated trials will have a normal distribution, almost normal distribution. So I'm doing the experiment, I'm tossing a coin, and I'm doing it, I don't know, like 100 experiments, 100 tosses, and the distribution is the number of successes, okay? So just to recap, if you have a discrete variable that is a repeated trial, let's say a binomial distribution of 100 tosses with a probability of success, I don't know, it's an unfair coin, of 0.6, okay? This is, if you take the histogram, if you take the PDF of this value of variable, so here you have 0 successes, 1 success, 2 success, 3 success, up until 100. Think about this. You can have no heads, you can have 1 head, 2 head, or you can have the 100 tosses coming up, turning up heads. Okay. And do you remember how we calculated the probability of this binomial random variable? Well, the way we calculate it is, what's the probability of your repeated trial be 0? So you have 0 successes. It's 10. I choose 100. I choose 0 to be heads, with the probability of being heads coming up 0 time, the probability of being tails coming the rest of the time. What's the probability of having 1 heads, 1 success? Well, I take 100. I select 1, I choose 1 to be successful, so the probability of having a heads will come up once, and the probability of having a tails will come the other part, which is 99. Do you remember this? We talked about this like 2 lectures ago. Okay? So if you plot this, okay, and the more you plot, the more trials you make, more the closer you get to a normal distribution. Okay? It could be tossing a coin. It could be doing a pregnancy test. It could be it's a normal distribution. Whatever repeated trial you're doing with 2 outcomes will be approximately a normal distribution. Okay. This is very, very important. So a large number of discrete random variables are approximately normal. Binomial random variables, specifically, they are, when you do lots of trials, these bins start kind of looking as a normal distribution. Okay? So what are we going to do? We're going to do the good approximation. We already know how to do the good approximation, I hope. So what we're going to do is an exercise to recap. So the IQ scores of the adult female population of Canada is approximately normal, with a mean of 100 and a standard deviation of 15. Okay, and you know IQ is measured. It's a discrete because you can have IQ 1, 2, 3, 4, 100. You cannot have IQ of 100.25, right? So it's just you're discretely jumping from one to another number, okay, integer number. So in the end of the day, what the exercise is telling me is that the IQ scores are approximately normal. Okay, they're approximately normal. using an approximation, find the probability that a randomly selected woman will have an IQ of most 104. So what do I want? X is the IQ scores for the female population of Canada. Okay. And what I want is what's the probability that a woman have an IQ of at most 104? Okay, that's what I'm asking. So I know that IQs, they are discrete. Okay, so but they are approximately normal. So if I do a mock histogram, if you remember the good approximation steps, the first thing you should do is a mock histogram. So if I do a mock histogram of the IQs, okay, I'm doing a mock histogram, I will have something that is very close to a normal distribution. Okay? What else that it said? It said that the average is 100. So the middle line, the mean, the expected value of X is 100. And I have a standard deviation of 15. So I'm kind of big spread. Okay? It's very rare to find a person with a 200 IQ, 180, which is like Einstein's IQ. And it's very rare to have someone with a very low IQ. Okay? So in general, people are within an average here in the middle. Okay? So what should I do to find this probability? Well, think about the good approximation procedure. You do the mock histogram so that you can find the intervals. So if this, so let me do this a little bit better. So let me zoom in. So what am I doing? The mean is here on 100, for example. Okay. The other bins will be like one by one. Okay. Again, I don't know how the histogram is. This is a mock histogram. But in the end of the day, I want to know the probability of having less than 104. So what's the area that I would select if I had the histogram? Well, I would select 103, this bin, and all the other bins. Okay, I would select all the other bins that are under 104. Okay, this is what I would select. Would I select the bin exactly of 104? No, because I never asked for this. Okay? I never asked for that, so I'm not going to put the bin in. Now, if you put a bell curve here, which it was told to you that is a good approximation. When you hear this term, you know that this bell curve will fit perfectly. Okay? Where should I start? If I want to select the same area under this squiggle, under this smooth curve, where should I select it to start or to stop, right? So I would start my area here, okay? So I'm just selecting this. I'm starting my area. Where should I stop? Should I stop at 103, exactly 103? Should I stop it here? Should I stop here and just get the area here? I would be missing a part, right, of this bin. I would be missing this part. So where should I go? Well, I should go up until the middle of the interval between 103 and 104, 103.5. Okay? So it's the same thing that we're doing with the good approximation rule. So is first, draw a mock histogram. 2, find the interval for the same area. This is what we're doing, okay? So in the end of the day, this probability here will be equal to the probability of going to the bell curve, which is a y. It's a continuous random variable. And saying that this continuous random variable is less than 103.5. Good? Now, can we look this up on the table? No, this is not a standard normal, right? This normal that fits this completely has a mean of 100 and a deviation of 15, exactly as the histogram, because it fits the histogram. Yeah.
So I'm just wondering if there's a way we can find the interval without making a long histogram.
You can reason, but I would suggest, like highly suggest, that you draw the mock histogram so that you don't get it wrong. Okay? Because it is not always a 0.5, right? It depends. If let's say if that IQ scores were jumping not 1 by 1 but 4 by 4. So you could have a IQ of 0, 4, 8, 12, 16, and so on. You wouldn't have a half. You would have 2.
Yeah, I'm just confused because like if we're drawing it, how do like we know that we're not drawing it wrong? Do you know what I mean?
So you're not so the heights of the bins, it doesn't matter. What you're drawing is what you're interested in is in the x-axis, right?
Yeah.
So it's a mock because you don't know the heights, you don't know exactly how the bins are distributed,
Right.
but you know that the bins are centered in the values, right?
Okay.
So you're not doing it wrong. If you do a mock histogram in terms of the x-axis where the bins sit,
Okay.
you are doing it right.
All right.
Okay? All right. So, can we, yeah.
I'm based off of her question, I'm still confused. Like, how would you know that when you're doing the mock histogram, how do you know that it's 100, 101, 102? How would you know that it's 101, 102 instead of 101, 104, 108? How would you know the difference?
So the IQ scores go 1 by 1, right?
Based off of this question, but if you're saying,
Yeah.
if we're making a mock histogram,
Of another variable, for example.
yes, and
Yeah.
you said that it may not always be 101, 100.
Yeah, so you could have a variable that is,
Like where would it indicate something like that in the question? Like where
yeah.
would it say?
So let's say that you have a variable, a new variable, that is the number of legs of a classroom. Okay, so it depends on the size of the classroom. You can, if nobody's there, you can have 0 legs. If you have just 1 student, you will have 2 legs. If you have 2 students, you will have 4, right?
Oh, okay, so it's because everybody can only have 1 IQ score? Like
Yes. So that's why I can go 1 by 1, and I'm centering my bins there. But if I have a variable that goes 2 by 2s, right? The way I would draw is this. 0, then 2, then 4, then 6, then 8. And I would center my bins around that. Because that's what a histogram means.
It'll either kind of like tell us that in the question, or we can just think about it and know, like, okay.
It will tell you in the question, right?
All right.
If it doesn't tell you anything, assume it's 1 by 1.
Okay.
Okay, so if I give you this, like this is a mock histogram, I'm not sure about the heights, but I know that whatever heights they are, the bins are, they are centered in 0 and 2 and 4 and 6 and an 8. Okay? So if I ask you, what's the probability of having less than 6? Well, I would be selecting this area, but not including 6, okay, if I want this probability here, because I never asked you equal to 6. So if I had a good approximation, a curve fitting, right, this histogram, where would I select the same area? Well, would I select it in 4? No. Would I select it in 6? No. To have the same area, I would have to go half of the interval. And half of, so I would be selecting exactly this. Half of the interval is 5. It's 4 plus 1, right? So this would be the probability of having a good approximation less than 5. Okay? And not, it wouldn't be 4.5. The 4.5, the a half interval, will only happen if your variable go 1 by 1. You always will be sitting on the middle of the interval, okay? But if your variable goes 2 by 2s, 4 by 4s, it won't be a half. It will be, I don't know, you have to draw it. Okay? Good. All right. So let's just solve this question. Oh my God. Let's just solve this question. How can I do it? I cannot. Let's go back. So we're talking about IQs, and I want the probability of this woman having an IQ less than 103.5. So what am I going to do? Well, I cannot look at the z-table. Should I standardize? Yes, you should. So you take y, you push this curve to 0. So you take off the mean of the curve, which is in 100, and you divide by the standard deviation, which is 15, and you do this on both sides. So you take off 100 and divide by 15. So this newly created variable is z, and this number here will be 3.5 over 15. I don't know. How much? 0.23? Yeah, I already did it. 0.23. 0.23. Okay. Now you can go to the table and just look. So let me open the table here. 0.23. Go to the row, find the first digit, it's 0.2. Then go to the column, find the second digit, which is 0.03. Cross both column and row. This is 0.6293. Oh, sorry. This is yeah. Thanks. This is 5910. Okay. So this is okay. So what does this mean? That means that the probability of having a woman that has IQ less than 104 is actually close to 60%. Okay? 59% something. Right? Yay, we finished! Yay! Yes, yeah, we did it. We did it on time, thank God. Yes, we have next week to recap. That's all. Don't forget that you have videos on online. It's what?
The online content also.
Yeah, it's yeah. I could come like next lecture and deliver the content, and we would still be good to do exercise in the last lecture. But my experience last year was disastrous. Like about delivering that content, specifically that one in person. Because it's just formula application. So it's a whole bunch of formula. And I started doing it on the board, and people just, they weren't kind of following, right? So what I did was I have two videos there. One is explaining the formulas. The next one is going through exercises really slow. And you can pause and you can go back. My experience tells me that it's better to do that. Okay? So just don't forget. All right, thank you guys. See you next week. Yay!